to start this recording. I'm going to start this if somebody else shows up. Somebody else shows up. Share that. Oh, so that's the beginning of chapter 12. So I put up somewhere, I think, the assignment for balancing and whatnot. That's the same thing that I showed, well, you guys yesterday. Um, and then we started this little thing. And this is fundamentally what stoichiometry is. It's about converting a mass of one thing to a mass of something else because we want to know how much could we make. When you do a reaction, yeah, it doesn't always happen as well as it should, but you still need to know how much should something produce. So stoichiometry, the metry is measuring, but the stoichio part is well, I don't know if that's measuring or the word means measuring elements. So quantities in a chemical reactions based on the balanced equation. So I have this kind of set up in terms of this is an old-fashioned but ridiculously important equation. It's just the synthesis of ammonia from the elements. It's one of the more probably most important industrial reactions because it produces ammonia, which you can go and make fertilizer and all sorts of things from. And some German guy named Fritz Haber, and there was a Bosch, because the Haber was the guy that figured out the way to do it on an industrial scale. Um, but it's got one nitrogen, three hydrogens, and you make two ammonias. So we can look at this. Well, there's two atoms of nitrogen. We mix that up with six atoms of that, and we get two nitrogens and six hydrogens out of it. Okay, that's all well and good, but we can one molecule of this, three molecules of that, give two molecules of ammonia. Well, that's more reasonable, but we can't do this on a molecule by molecule scale. Well, how about 1 mole? If we take 1 mole of nitrogen gas, which would weigh 14 and 14 is 28, 3 moles of hydrogen gas, we would produce 2 moles of ammonia. Well, I can do that with mass because we know this is 14 twice is 28 grams. We have to do this proportionally 2 moles because I can't do 1 gram of this, 3 grams of that because this weighs significantly more. So 3 moles of hydrogen would be about 6 grams. 14, 15, 16, 17 twice would give you about 34 grams. So this is the key because we have 1 mole of this, 3 moles of that, 2 moles of that. It's always going to go proportional. If I have half a mole of this, well, I'm going to need 1.5 moles of that, and I would make 1 mole of that. But I can do it, I can scale it up and say 10 moles, 30, and so it's always going to be in that same ratio, and that's what is the important thing. So if I start with 10 grams, I can figure out proportionally how many grams of this I would need and how many grams of that I would make. Um, Conservation of matter, mass. Mass and atoms are conserved. We're not doing nuclear physics, so we're putting things in the right order and all of that. So the ratio of molecules and moles remains the same as the stoichiometric ratio in the balanced equation. So this is kind of another example, 2 hydrogen chloride gas decomposing into hydrogen and chlorine. The mole ratio, well, we have 2 moles of this, 1 mole of that, and 1 mole of that. So this is the same idea as what we just talked about. If there's 1.4 moles of hydrogen chloride decomposed, well, because 2 of this, we're cutting that in 2, this is only going to be 0.7 moles, and this was only going to be 0.7 moles. If we do the mass, which we'll talk about probably next week, because maybe at 9 we'll pick up some more people. The typical type of question, the first simple question is how much hydrogen chloride gas is required to if 3.5 moles of chlorine gas is produced. So even though this equation starts with hydrogen chloride, we have a number. Whatever number you're given in the question starts up here. Oh, I'm going to use a different color because that's 3.5 moles of chlorine gas. In the calculation, I'm not super worried about the state, but we can put that there. It's the same as a conversion. How much hydrogen chloride gas is produced? So what we have, what we want. So this intermediate step we usually refer to as the mole ratio. And there's no really kind of universal thing. You can kind of look at it. It's always going to be the unit you want in your solution over, well, that was supposed to say unit. You have. Well, what unit do I have? Moles of chlorine. What unit do I want? Moles of HCl. So now we need to find these numbers, and this ratio comes from a balanced equation. In the balanced equation, we have 2 moles of HCl, and even though it's not written, 1 mole of chlorine. So whatever coefficient is in front of here, 1 mole of chlorine, 2 mole, whoops, 1 mole of chlorine for every 2 moles of hydrogen chloride. So there's what we set up. Moles of chlorine and moles of chlorine cancel. Same as when we did grams and moles, which we'll get to eventually. 3.5 times 2 is 7.0 moles of chlorine gas, which for an equation like this, which is 1 and 2's, most people are see, well, 2 moles of this produces 1 mole of that, so I need 7 to get 3.5. And that's kind of the basics of stoichiometry. You have an equation. You want to convert one thing to something else. So there's a couple more things of this. Oh, and then apparently, why go away? That's what I would probably normally ask you to do before we do gravimetric stuff. The mole ratio, 1 mole, 3 moles, 2 moles. Well, if I'm given 1.2, how many moles of each one? Well, I can intuitively go this way. 1 mole of this needs 3 moles of that. So am I going to multiply by 3 or divide by 3 to go from this, from hydrogen to the nitrogen? If I multiply that by 3, I get 3.6. That doesn't seem to make sense because there's less of this to that. So I'm going to divide by 3. So we would need 0.4 moles. And then if I was doing this without setting everything up, 1 mole to 2, so I'm going to produce twice as much ammonia as I have here. we would produce 0.8 moles of ammonia. Normally, the questions that you're going to be asked are on the, here's an equation. How much ammonia is produced if 885.3 moles of nitrogen is reacted with excess hydrogen? So that tells us this is necessary but unnecessary information. Excess hydrogen, so that means we have more of that than we need. We're never going to worry about how much it is. If there's 800 moles of nitrogen, there's 15,000, 20,000, 200,000, whatever, moles of nitrogen. It doesn't matter. There's more than we need. So 885 point moles of nitrogen. How much ammonia? Well, moles of ammonia. So if I put my little, no way. What I want, well, what we want is moles of ammonia. What we have is moles of nitrogen. Then we go back to our balanced equation. 2 moles of ammonia, 1 mole of nitrogen, 16, 17, 1770, 885.3 times 2. Now, there's 1, 2, 3, 4 significant figures there. This number has 5, so by the rules of rounding, we would get 1,771 moles of ammonia. And this is the kind of first step. This is the chemistry quantities. Well, chemists understand moles. If you go to any chemistry department and say something about moles, they understand. You go to certain plants, if you go to the oil refinery and they're doing something, there's some people there that know what moles are, but they don't work on moles because, well, it's not something every day. So there's usually a step at the beginning to convert some amount to moles, which we already have grams to moles. Technically, we've got some pressure volume, or yes, technically volume to moles. So we can add a step on this end. We can add a step on that end. And that's fundamentally as complicated as it gets. We're going to add a step on either end, and that's really, but this is where the stoichiometry is. This is the stoichiometric ratio, converting moles of something to moles of something else. That's what stoichiometry is. Still just you guys. So, oh gosh, I can make this a little bit trickier. Balance it. That's some sort of dodecane. 12 carbon. Oh dear. 12 carbon. 26 hydrogens. 26. 24 plus 13 is 37. That doesn't compute with that. So when we go back to balancing, we double this. 24. That is not 16. That's 26. So 48 plus 26 is 60, 74, ironically, half of which is not 37. Writing, sorry, it is 37, it's not 34. Whew. Friday, thankfully we're almost done. So the mole ratio, wow, they're crazy big numbers. 2, 37, 24, 26. Two and a half. Well, that gets, this is going to be a little bit tricky, but if I want to know moles of this, I'm going to multiply by 37, multiply, and then divide by 2. Why did I pick that? 2.5 times 37 divided by 2. If I have 2.5, we would need 46.25. And this is not really 24 times, whoa, 26 times 2.5 divided by 2. That was weird. I don't know why that turned red. Because it's a multiply and divide. Because if I want water, I'm going to multiply by water. And that's not really a question I would ask. I would probably give you one like this. If I have 100 moles of water, how much dodecane would we need? If you wanted to make 100 moles of water, each mole is 18 grams, so to make 2 liters of water vapor, give or take, no, a little less than 2. We set everything up. What do we want? Moles of C12H26, moles of water. We go back to our mole ratio. Now, a couple things with the mole ratio. 26 over 2, can you simplify? Sure. Like, that's not a hard thing to do in math. In chemistry, leave this because I know what the balanced equation is. So I know what numbers I'm looking for. If you all of a sudden have 13 and 1, if I'm not paying attention when I'm marking or whatnot, I may miss that. This is now that there's a 2 here. If I'm doing this with a calculator, 100 times 26 divided by 2. Technically, that's 3 significant figures. I've moved that 3 spaces. To have 3 significant figures, I technically need that, but it's 1,300 moles of water. Even though that's going to weigh significantly more than that. But 1 mole begets 13, 2 moles begets 26. So we have this, the mass is, sometimes you're going to have things where you start with a gram of something and you produce 100 grams of product because of the other parts to the equation. Now, what are the odds? I can find and see what some of those questions look like. Textbook scans. We're on chapter 12. Obviously, that's just conversions. That's basically the same example that we've done. Interpret. What are the mole ratios? What are the mole ratios? I don't know where. Oh, 12 is more a mole ratio. Write 6 different mole ratios because we've got 4 over 3, 4 over 2, 3 over 2, 2 over 3, 2 over 4, 3 over 4. Something as simple as that technically has 3 different bits. Now, Why did that not want to... There's no way somebody scanned this and locked it. You've got to be kidding. I wanted the locked part. I already have it locked. Wow, way louder than I thought. Where did I go? So it says 6. So we have that equation. That's just aluminum oxidizing. So it says there's 6 because we have 4 moles of aluminum over, or for every 3 moles of oxygen. But that, well, I can't say equals because it's not equals. Even though this is the same ratio, technically they're different because it's the ratio of aluminum to oxygen. For some people don't put moles in there. I like it. And even though those are fractions that you can simplify, because it's a mole ratio, we don't actually do it. So we need 3 moles of oxygen. So B and that part, how many moles of aluminum are needed to form? 3.7. Well, that's what I've got moles of. I've had the odd time people start putting numbers in. Oh, well, it says I want to form this. Well, so it's got to be at the end. It's like, no, no. You're given a number in the question. Start with the number in the question. We want mole. We're given that. We want moles of aluminum. So what I'm given goes on the bottom. What I want goes on top. This one is AL and AL203, so it's 4 over 2, 3.7. Now, if you know that it's a double, because I'm never going to see your calculator, do you have to do 3.7 times 4 divided by 2? No, because I'm never going to see your calculator. Now, if you're good at math, you can get away with it, but there are some people who don't. 7.4 moles of aluminum. So if you want to practice a couple, you can try those two, and I'll on Monday, well, Tuesday, nothing on Monday. We'll go through and give you the answers of those two. But that's the first step to stoichiometry. Then we're going to tack something on the beginning. What is the mass of carbon dioxide produced by 1,000 grams of methane? So we have to go from mass to moles. Well, we've done that already. Then we have to go from moles to mass at the end. And then we'll do a few examples of that. And then there's some practice. But that seems like a nice place to stop on a Friday afternoon so we don't rush and try to get everything missed. Plus, well, I mean, you guys are here and you guys are doing the work, so it's the rest of the people that I wonder about. So we'll stop there and I'll change the meeting time to 9 o'clock, which is probably going to freak some people out. But if you're not showing up at 2 and the people who are at 2 want to go to 9, why not do it at 9? Sound good?
Sounds good to me.
Perfect. Well, have a good weekend.
Good weekend.
You too. Enjoy the sun on Sunday and Monday because it's
You
not.
too, Mr. McKay.
Thanks. See you later.
Bye.
Bye.